All right, in this video, we're going to talk about metallic bonding, and we use the word sorta here because when metals interact with each other, they really don't undergo any chemical bonds. But we still want to call it metallic bonding because we are talking about that interaction between one atom of a metal to the other atoms of those metals, okay? So first thing we want to talk about is realizing that metals also form crystalline structures. So very much like ionic compounds, they're going to form some sort of very organized structure or pattern to it like you see in these two images over here, okay? One key difference is that for metals, we have the electrons not held nearly as tight, okay? So for ionic compounds, those electrons are very much, transferred from one to the other and very, very bound tightly to those nuclei. For metals, the nucleus does hold the electrons, especially those valence electrons, but because they are not held as tight, they can actually flow from one atom to the other. As long as there's an average number of electrons, relatively speaking, in the same positions, they're good, okay? We call that ability to flow, or this idea, the conduction band, and we'll see that in a little bit in our next slide, okay? Now, the electrostatic force between the stationary nucleus and the flowing electrons is what holds it all together, okay? So you might be thinking, well, if there's no positive ion and no negative ion, how does this group up and form this structure? Well, we still get this effect where these positive nucleus are going to attract these electrons, and because those electrons are moving from one atom to the other, there's always kind of like this binding effect that kind of happens within metals and kind of holds them all together, okay? Please do not call this a chemical bond. It is not a chemical bond. If you had to relate to something, it's more like IMF, okay, or more like an intermolecular force that kind of holds these metallic crystals together. But it is still crystalline structure. So with that crystalline structure, we do get some strength out of that, okay? The big thing to remember too, we know it's not a chemical bond because when you place metals together, we do not change those individual properties. So you put individual atoms together, even if they are different metals, each metal still retains its own properties. Okay, so that brings us up to talking about the conduction band theory, or how or why can metals have electrons that are able to flow from one atom to the other pretty seamlessly, okay? And the idea is this, that for metals, if you take a look at the red versus the blue here, the blue would be the last orbital of one atom of metal, and the red would be the last orbital on another atom of the metal. And those last energy levels actually overlap each other, okay? So those orbitals here are overlapping. So for metals, if I'm an electron here, I can just go fly over here and come back over here again, okay? If you're a semiconductor, we see this as there being a very, very tiny gap between the orbitals, okay? And as a result, the electrons can't just flow freely between the two orbitals, but they can jump from one side to the other if they have enough energy to make that little jump, okay? Now your insulators, like your nonmetals, okay, what we say is there's like this huge gap between those. We call that the band gap, actually. And what happens is you have electron here, it can't make the jump. It tries to leave and it gets sucked back into that atom. This one over here tries to leave and gets sucked back into that atom. So as a result, the electrons can't flow from one atom to the other. And as a result, you have insulators here versus metals where the electrons are free to move from one atom to the other one, okay? Now, if we take a look at the same thing on my iPad on an image, I like to kind of draw it up as more like these kind of clouds instead. So if you take a look, if I was an electron right here, and I was a metal here, as an electron, I could cross these overlapping orbitals right here without any problem. I can kind of move any way I wanted to through this thing, and it wouldn't make a difference because I could travel from one spot to the other. Now, as I'm an electron and I am moving, the other ones are also moving. These are all moving around within each other. As a result, we get this conduction that can happen, okay? For nonmetals, you have an electron that starts off, it tries to leave, and it experiences a gap here, and it gets pulled back in, so it can't leave, okay? This electron tries to leave, and there's a gap here, so it can't, so it gets pulled back in. So because of these gaps between these atoms here, okay, or the band gap, they're not allowed to flow. So these are going to be our good insulators, whereas our metals are our good conductors, all right? Now, there is a result of that kind of makes metals a little bit different for us, okay? Because of these mobile electrons, first of all, the positive nuclei are able to slide past each other, okay? I'm going to kind of show you this in this next image. So this is kind of like another drawing of what I just did on my iPad. Here's kind of an idea of visualizing it. If you take a look, it's almost like we have a whole bunch of positive nuclei and just kind of a sea of electrons. And those electrons can be pushed and pulled throughout all this, kind of can move around where they need to in here. Okay, so imagine if you are a metal and all these positive nuclei, and if you strike that metal, okay, remember for ionic compounds when we did that, the positive and the negative would line up and cause repulsion, and it would crack and break the ionic compound apart. Well, for metals, because it's plus, 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 if I push this plus over to here, oops, let me go back to that. If I push this plus over here, nothing really changes, okay? So they can slide past each other because they have all this negative charge in between them, okay? As a result, metals are more ductile and more malleable, which means you can bend and flex and dent and kind of mold them into different shapes because their atoms are allowed to slide past each other, okay? With some resistance still, but not nearly as much we saw for ionic compounds where they were brittle and they cracked, okay? As a result of this too, we get two other phenomenon. One, electricity can be conducted really well for this. So you have if you put more negative charge in, you actually can push electrons in one direction or the other. So we actually can force the electrons to flow one way we want to. Now they're going to randomly flow on their own, okay? There'll be no net change. But if we create a positive terminal and a negative terminal, we can actually make those electrons kind of align and move the way we want them to move, and that's conduction of electricity, okay? As a result, we get some properties of metals we want to talk about. First, metals can conduct both heat and electricity well in their solid form, okay? And it's really key here we say that in the solid form, because they're the only substance that can do this in the solid form really, really well, okay? They're going to be more malleable and ductile than their ionic or molecular compounds in comparison, okay? We can bend them, we can shape them, we can melt them down and kind of give them new, not properties, but new like structure to them because of this. Now, in terms of their melting points, they do form a crystalline structure, but it's not as rigid as ionic compounds and not as strong. So as a result, they're going to have lower melting points than ionic solids, but typically you're going to see that metals still have higher melting points than molecules, okay? So molecules tend to even be weaker in terms of how they build structure between the molecules anyway, as we do these. So if you're ranking them, ionic compounds are highest, then metals, then molecules, okay? And one thing that they can do is metals are able to blend with other metals to form alloys, okay? So you can take copper and nickel or copper and zinc and make brass and bronze and other different types of alloys, okay? One thing to make a note of, make sure, when you're looking at this idea of forming alloys, we're going to create a blend of those properties between the two metals, okay? So you're taking the metallic properties of copper, the metallic properties of zinc, and putting the two together, and as a result, we're going to get brass. Now, when you do that, you don't have a whole new compound with a whole new set of chemical properties. It's more a blending of the individual properties between these metals. Okay, that creates a more desirable effect or a better metal overall. Okay, so then how do these alloys work? All right, we already know it's a physical mixing. Okay, so make sure we kind of highlight that because this is not a chemical bond here. And within that, there's actually two ways you can form alloys. Okay, if the atoms of one metal are similar in size to the atoms of another metal. Okay, and we kind of have a good idea of how size works now according to our periodic tables. So if those atoms are similar in size, one metal will actually replace the other one in its kind of structure. So if you look here, you have like a bunch of zinc and you have coppers replacing it. You don't have nothing else in between them. So the copper actually takes the place of where you would normally expect to see a zinc. Okay, the better you blend the alloy, the better you make this work, the more uniform that structure can be. Okay, things like brass and bronze are considered examples of substitutional alloys. All right, and these ones do that substitute. Now, interstitial alloys are ones where you have one atom small enough to fit in between the other atoms. So here we have steel or carbon steel. So we're actually using carbon, and carbon is actually fitting in between the iron molecules here. And as a result, we're getting, you know, your normal iron and then all this extra structure that fits inside of that. Okay, that extra structure creates a very different product. Okay, where we create steel is a good example of that. Okay, Now, it is possible if you start blending 2, 3, 4, 5, 6 metals together, you may get a blend of both of these. You get some substitutional and some interstitial action going on. Okay, an example of that would be stainless steel, where you're going to blend in a couple different metals. I didn't have a picture of that one, but you have blended a couple different metals together, and you're using things like indium and cadmium within the iron, and they're going to be substituting with the iron. And within that, then you're going to add in the carbon that adds that effect to it. So you can actually have a combination of both also when you're making alloys, all right? One of our labs that we do often is to create an alloy, and we'll be doing that here in a few days, all right? Now, one thing to remember, do not forget that this is metal plus metal, okay? For ionic compounds, we had a metal and a non-metal, okay? When you have metal and another metal together, it really doesn't form a new compound. It forms an alloy instead when it's metal to metal, all right? Now, that brings us to molecular bonding, so we're going to end the video here and do this one next one. Thanks.